Hello everyone, it is July 1st, 2025, and this is the bi-weekly libhal meeting. Alright, some agenda items for today. We're going to go over a couple of things that we're working on, and then go over some of the hard problems we've solved, some of the new problems that exist, and then I think I'm going to go over a couple slides for coroutines, then we're going to cut it there because there's not enough put together yet. But first, I'm just going to talk about libhal-mac. I made some upgrades to, or added some new interfaces or implementations for the RMD drivers, so the smart motor controllers. Um, I was getting kind of annoyed having to pull out the HAL board or some microcontroller with a CAN transceiver to connect it up to the device and then program that device and see if everything works at that point. It'd be really nice if I could do all my debugging from my laptop. I've always wanted to extend libhal to work on the laptop, but at this point I felt that this was probably the best time to kind of make this happen. So I spent some time, got some drivers made. Most of the drivers are actually written by Claude, or specifically the serial driver and I think a static clock driver. That I had Claude make that because it was mostly just boilerplate C++ stuff, not stuff that it could really mess up. And then the Mac serial port implementation, I might upgrade and fix that up, but basically that's what we have for that. But there's also basically we made some drivers for Mac that we can use to connect to other things, which then brings us up to our next item, which is HAL Expander canusb. This is a implementation of the canusb protocol or serial protocol. Thus, if you had some serial port that was connected up to a canusb device, and you had a driver for that same UART or serial port, you could pass that to the HAL Expander canusb driver, and it will be able to send CAN messages as well as receive CAN messages. I don't have filter control yet, but you'll be able to see all the messages in general. So with all of that, I was able to test out my code for the RMD motors without needing to pull out a microcontroller at all. I think that's something that I think is really cool. I want to do more of that kind of stuff. We already have libhal Linux, which can do that. I want to libhal Windows, which also has serial port type communication. And just kind of build out a whole suite of different types of libraries that effectively we talk over serial, and then we're able to do certain actions. That way we can do a lot of testing with that platform, and then when we really want to get low latency and lower power and that kind of stuff, we can then move it to the MCU. All right, so that's me just talking about these two new items. They're in the process. They're in the pipeline. Now for some of the hard problems that we've solved. So I'm going to go over a couple of things that I've talked about in the past that we've actually figured out at this point. One of them is USB enumeration stack. I was really concerned initially about how we could make such a complicated system work with our interfaces and still feel as if the network of interfaces is still very free. There is a reason and purpose for each one of the interfaces in the USB stack, but it doesn't feel like this. How should I put it? It doesn't feel like it's a framework that you have to buy into to some degree. You get a lot of control and flexibility about when you send messages, how you send messages, how you want to schedule that, all that good stuff. So we figured that part out, and that we're pretty happy with that. Another one that I figured out recently, and I kind of just kept this to myself just because I just never did a write-up for it, but TLS support. With some Googling and a little conversation with Claude, I was able to figure out that if we take the TLS model local exec, I'm pretty sure that's the right one, all we have to do is implement the EABI read thread pointer function. We can implement that. And we can implement that for our platform, or we can implement that for our particular operating system. So for example, if you have FreeRTOS, we could take up some of the thread local stored memory and then map the read thread local storage pointer and point it to that. Although most likely we're going to do something a little different because that might not be the most efficient way to do things. So there's that. And yeah, I'm also hoping that like, and I already have an idea of how we can implement a default linker that will allocate memory in RAM for the main thread's TLS. Basically, we would just pull in the linker, provide a block of memory that is equal to the size of the whole TLS memory section, and then we can do the when we first boot up, we can copy those values over. Um, and I think actually picolibc might already have some capability built in to kind of do that by default. I'll have to look into that, but if not, we can easily make that happen. Polymorphic catch is another one. Um, Something we figured out a while back that that actually wasn't as scary or as daunting of a problem. Lifetime management. Uh, I I think I've gotten a lot of OKs from everyone I've spoken to about this. I just haven't really pulled the trigger because I don't want to just make the code even more complex to think about. But basically, when it comes to lifetime management, it's come down to using smart pointers. We built our own strong pointer, optional pointer, and weak pointer. Strong pointer is our version of a shared pointer. Optional pointer is a shared pointer but can be null. And then weak pointer is like a weak pointer to shared pointer. Um, the only thing that you have to make sure you keep the lifetime in a good state would be the memory that you're getting for storing all of your objects. But if you make those static, then you don't have to worry about anything because it'll be fine unless you run out of memory. But then you'll figure that out because the code will throw an exception for that. But yeah, no. So our solution to lifetime management is basically to put things in places where they're most useful. And this actually has a whole slew of really awesome benefits. It allows a lot of our code to be snuck away into source files now. Before, we couldn't easily pass back a pointer to an implementation. Before, if we wanted to do that, we would have to statically allocate that somewhere. And normally it would just be wherever the linker places it. I didn't really like that. I wanted people to have a little more control over where their objects get placed, which is why I tried to move away from that and to make sure all of our objects are well defined so you can just place them on their stack or on your heap or wherever. But now I'm getting to the point where I think that the only thing that should be on the stack are things that are temporary. The only thing that should be statically defined, the least number of statically defined things should be statically defined, just so that you don't end up having things that like take up memory and aren't useful at all times during the program. I think smart pointers are the right way forward for that. After that, API doc version control. We have that working pretty well. I'm pretty happy with it, except for the fact that I also realized that it's kind of useless if you don't also add in the markdown files that are necessary for it. And what we really now need is a way to automate making the MD files, and then you specify, like, I want to put this class and everything about it and all these other information about it into, or this file in this particular location. There's probably a way to automate this, probably just with a script, but I'm also thinking that maybe a large language model might solve that for us as well. Previously, dealing with halting drivers was to use IO waiters, and the idea was that the IO waiters would be able to throw exceptions, and that's how to get out of things. But then I realized that what I was creating is, I don't know, it made me think, well, if we need to use exceptions to get out of everything, maybe I should consider looking into coroutines to see if that's not the better option. Coroutines were developed explicitly to ensure that exceptions or threading something to change the context were not utilized in order to make them work. And I think that's actually a fantastic aspect of them. And I don't really like the idea of using throwing for timeouts and throwing for getting out of halting. Like, it makes sense when a system's locked up to throw, because that is a problem, that is an error. But I didn't want that to be the only solution for halting drivers or calling abort. I wanted there to be a way that the system could continue to operate and detect that and maybe even handle it. And I think coroutines gives us that. Here's a couple other items that we haven't figured out. So going over to the new hard problems, automating the docs for rendering is a problem. I think a large language model could be a way to actually solve this problem. That would be kind of neat. Just because like we could have it like put in the actual text, explain to it what we want it to do, have it implement the actual files by looking at our files, and then giving a small little description of what this particular thing does. I think that'd be a good use of large language models. especially if you keep it really short and narrow on what it can actually talk about. Implementing coroutines. I am feeling every day I work with them, and every day I come up with better ways to implement things, and not like in a early optimization way, more of like I need to expand the system a little bit to open up the capability for generators. Um, but that's still ongoing because I'm still trying to make sure I get the last little bits figured out, especially how I'm going to handle some other things. Display interface is still, we're not sure how we're going to go about that. I think we had a pretty good idea actually how to do this. Me and some other people who were working on it have an idea, so there's that. Search interface, actually we already still have an idea about how we would do that too, but we haven't fully implemented it and like done the full research. And finally, construction and resource management. This is what we're actually going to talk about in a sec, and I think it's actually the next slide. Yeah, we're actually going to talk about this right now. I have come up with a few different ways to do initialization for stuff in libhal. And I was looking at what we currently have, and I still wasn't really happy with it. And I know people are going to hate me for wanting to change things again. But I was looking at something like this, and I thought to myself, how do we go about making all these things and plugging and plumbing them together? Like, what does the code look like for that? And right now, it's usually like you construct this object, and then you pass it into this guy, and then from there, use like acquire temperature, acquire voltage, acquire current, and then he passes on to other things. That works. There are a couple of things though I don't like, which is one, these objects aren't allocated as smart pointers, and having things that can get dropped out of nowhere and have them be deleted if that happens is problematic, so I don't like that. Another thing is the acquire syntax. I came up with it just because I thought it'd be nice and flexible just to have classes that like gave you back stuff. But I think the discoverability becomes a bit of an issue. I think it becomes a bit annoying to have to write, and I think and sometimes anyone could change what they name any one of those methods. And I don't want to force developers to have very strict requirements on how they type those things out. I mean, I do, but I also like don't want the chaos that would be adding in the additional inherited headers to make all that stuff work. So, without further ado, I think I've come up with what I think we'll probably stick with for a while in terms of how we create drivers and subdrivers and drivers that come out of other drivers. And that is simply this. Top level managers and objects will have a create method, a create static function. So it'll be whatever platform or driver or thing or category you're in, the name of your driver, and then create. You'll also pass in an allocator or a memory resource, which will convert into an allocator. And then whatever configuration this thing needs, like whatever parameters you need to give to this thing. Out will come back a HAL strong pointer of whatever object you wanted to construct. The normal constructor for this thing will be private, and you'll only be able to access it through this. And this is just to ensure that whatever you get back out is a smart pointer, basically. And the reason why we do this is that this will pretty much eliminate all of our memory safety issues. Any strong pointers or allocated stuff that ends up on the stack that doesn't go anywhere just gets cleaned up when the stack goes away. But everything else that wasn't will still persist, and then that'll go on until if your program runs forever, then it'll run forever in that way. The same idea here is that we only do this during initialization. We get everything set up, and then we go stable from there. That'll continue to be the case, but now we actually ensure that if you have a strong pointer to something in your object, that thing is valid. It's never not valid. Now, so my idea is to go back to create functions or factory functions. And then on top of that, to kind of go back to make functions, but this time kind of call them acquire. I felt like the acquire name made more sense to acquire some resource out of something bigger. So you give it an allocator. This would be the allocator that you would use to allocate this object's memory, the smart pointer for it. The manager is this guy, and this is used for two things. It defines which version of the acquire function you get, because it'll be disambiguated based on the manager. Also, the arguments you put in here as well. But the manager, the allocate and the manager is what kind of separates it out. So the style for this will be, if you needed, like, let's say a temperature sensor, and I don't know if I have a line for that, but if you had a temperature sensor, it'd be acquire temperature sensor. You put in the allocator to allocate the temperature sensor. You pass in the manager, which is the thing that you want to acquire a temperature sensor from. It'll call the factory function that then uses the manager to generate that thing and then returns it back to you. Then you can take that resource and pass it to something else that needs it. The reason why I like this a lot is just because this is kind of finite to the thing you're trying to create, but then this is consistent everywhere. Anytime you see acquire temperature sensor, acquire velocity servo, acquire linear actuator, acquire accelerometer, acquire output pin, you know what you're going to get back out, at least to some degree. I might make some slight tweaks, or I'm still coming up with the policy for what this thing should return. In general, my feeling is that this thing should return to you the strong pointer to the thing that is the interface, the thing that implements the interface, or it should return to you an array of such things. And the idea is that sometimes you ask for a thing, but you end up getting 4 back, just because that's just kind of the nature of that particular hardware. One example of this would be can filter IDs, I send them back in groups of 4 because trying to split them up any further would be very complex code-wise, but keeping them together as a group of 4 is actually perfectly fine. So there will be cases where you might return back not one thing, but a set of things, a set of resources. Then you can pull out which ones you actually want, and then you can go from there. Most likely that entire thing will be wrapped inside of a strong pointer, such that when you pull your separate resource out of it, the whole ensemble exists and persists. Yeah, that's more details on that when we kind of get to those points. But for now, it doesn't really matter. I will ask after the meeting, after we kind of close the meeting and we stop recording, how people feel about this. Because maybe I'll change maybe you guys can change my mind. All right, we're gonna go into a little bit about coroutines until I feel like it's no longer comfortable or I no longer feel like there's concrete stuff to talk about. But first, I just wanted to talk about what coroutines are. Just restating this is that C++ coroutines are functions that can be paused and resumed. Normal functions allocate their stack frames on the stack, meaning that when one function gets called, it will move the stack pointer down, and the space between where it was before and where it is now is memory that it will use to hold all of its local variables. When that function calls another function, it releases control, calls the next function, and then it allocates its own memory. When that function ends, it moves the stack pointer back. Now the memory's been deallocated. With coroutines, because of their asynchronous nature, the best way to kind of handle them is to actually place them somewhere that's more persistent than the stack. If you tried to use a stack with coroutines, anytime you context switched, well, you have to have some sort of context switch because you couldn't pull or migrate the entire stack of your entire frame each time you want to switch to something else. So they usually put it on the heap, but we have the opportunity to choose our own allocation for this. And that's what we take advantage of, actually, so that we end up producing or providing our own stacks for each one of our top-level coroutines. So why coroutines for libhal? As I dug deeper and deeper into this, I realized the strength and the power and the benefits of C++ coroutines. I think they're really neat, and I think they open up a whole world of really awesome patterns that we can build. And the fact that it's so, even though I'm building up this whole system, this whole asynchronous architecture, I still feel like even with that architecture and its constraints, it still leaves so many different options for how people can curate and control doing their I/O and doing their asynchronous operations. So, coroutines provide a consistent language. So having coroutines in libhal would provide a consistent language-supported means to produce asynchronous code. Like we showed before, you have the co-await expressions and that kind of stuff, and that all looks like normal synchronous code. But the cool thing is that from the caller's perspective, if you're in synchronous code, you can if you wanted to, you could run those two things concurrently. You can get them both started and then increment through each one back and forth, context switching between either one. Um, or you can do a whole variety of other options with it. But the cool thing is that you get this opportunity to control that whenever you want to, which I think is really neat. Um, Also, one thing that's also quite common is that it's usually easier to make asynchronous code synchronous than to try to break synchronous code into async chunks. That was kind of what I was trying to do. I mean, really, that's what you do when you use an RTOS. That's really what you do when you have when you use like exceptions to get out of your stuff, or yeah, basically you're trying to take synchronous code and break it out in some way. Whereas if you use coroutines, you're building in the exits and entries into every single part of the code, which has quite a few benefits. Keeping errors out of that space, I think, allows for a lot more optimal code, because you don't have to worry about propagation. You just kind of just go forward and go forward and go forward. In a way, I don't have return blocks everywhere in my coroutine code, or at least not in certain areas, because I've designed it to ensure that once something kind of completes, you kind of just go through and, yeah. Anyway, it provides suspension points throughout the code, which can help reduce the chances of system deadlock. Like if you have a while loop, or you're looping for something, if we built up the code and have good policies on how you write code for asynchronous operations, such that we won't see any while loops, or we might see while loops, but we will see while loops that have that suspend themselves. So they'll loop up to a point they say suspend, and then they will jump out, let you control other things, and then you can go back in, and then you do that loop again. But you're not really stuck in the loop. You're only in the loop for one iteration before you can do something else. So that's kind of the cool thing, is that you get that kind of control. So long as I've been noticing that if you attempt to use mutexes or anything else like that within a coroutine, it can be very dangerous, because if you lock your entire thread, you can't run any other coroutines. You're stuck. And I think my favorite thing that don't have any slides to show you right now, and I'll probably show the next couple bits here just so it's available just out there, but one of the things that I really like about this new setup is that it gives us a way to abstract out what it means to delay for a certain amount of time. So I want to go over a little bit of the architecture of libhal coroutines. There are like a couple of sections that you have to kind of keep in mind of. So C++ coroutine frames need to be allocated somewhere. So that somewhere that we provide is called an async context. This provides memory for the coroutine frame, as well as information about what its block state is in. So on top of also managing like the memory for each one of the coroutine contexts, I realized that it makes sense to report information back to the application about the state of a particular coroutine, and to use a handler for that. So give it a callback, basically, a callback function saying, pass me what the new state is, pass me the async context so I know which one is changing, and maybe also a time frame for how much time this thing should block for, and then I can do something from there. So that's what you get from async context, what your block state is, and also where to allocate your memory. And this kind of just says the same thing. Every coroutine function in libhal will have to take async context as a first parameter. It is annoying to have to do that. I agree, but it's also what enables us to get asynchrony. So it's kind of just an aspect of what we have to do. I like to think of it as passing along, and it's by reference, so it only takes up one register. But I like to imagine it like passing down a stack pointer, so it knows how to continue on. You can't create an async context by yourself. You need to create an async runtime in order to create an async context. So the async runtime takes a value or a number n, and it stores the count of async contexts that you want to create. So you can say I want like 3 of these, so I want to be able to do 3 things concurrently. And you also need to pass it a transition handler, which knows how to handle what happens when the state changes. And then finally, we have this thing called future t. This is the return value for your coroutines, and I'll show you what that looks like in a sec. It's cool because it can be a variant. It can either be a C++ coroutine handle, meaning that it represents a pointer to a stack frame that knows how to do some work. So you can execute that particular thing. When it's complete, it changes its state from a coroutine handle into the type that you wanted. So it's a handle, and the information about where that handle is located or where that future T is located is passed to the coroutine. And when that coroutine finishes, it updates your object to be the type that you wanted, the result of what you're looking for. So let me see if I can kind of show this example here. I don't know why I positioned those slides in this way. So we have some HAL future, HAL Celsius. So you're just going to get back some Celsius value. You get some temperature, you're going to get a context, and you're going to get an I2C using a strong pointer. When we upgrade to V5, the V5s here will go away, so you won't need to have those anymore. This should also have a V5 in front of it, but I think I just forgot to type it in. So let's say we have some temperature sensor on I2C port 1 and I2C port 2, so they won't conflict with each other. What you can do is you can pass a context that we created somewhere else, pass one in, pass another one in, and get back these two futures. And there's two ways you can go about doing this. You can either just like call it, pass it in, pass the item, and then do sync wait, which will do two things. It will call, resume, and it'll continue, basically it'll synchronously execute the operation until it's finished, and then return back to you a result. And same thing with this one. This will happen at one stage, this will happen at the second stage. If you wanted to do them concurrently, one after another, you could have a little while loop here, and you can do, all right, check to see if the first one's done. If it's done already, we don't need to worry about it. Second one's done. If it is done, we don't have to worry about it. We can break. If not, check to see if future 1 is not done. If it's not, resume it. Check if number 2 is done. If not, resume it. And you keep resuming these over and over and over and over again until eventually they're both done, then you can get back the results. There's a result function here that you can grab. There's a safe and unsafe one. Sync wait's also another way that's safe. Yeah, so that'll get you the result out from here, and then you can actually use it. But this kind of shows a way that you could go about doing this asynchrony. And it's really as simple as this. You have a done function, you have a resume function, and you can call those whenever. When you call resume, it'll execute that function up until the point where it sees a call wait, or until like it realizes that it can like wait for a certain amount of time. Now the full showing of this would be this back here. So in order to actually plug into this, you need some coroutine stack memory. You need some memory that will hold your coroutine frames. You need to give this to a memory resource. So in this case, we're using the monotonic buffer resource. Give it the pointer and the size, and we have it fall back to the null memory resource, which will throw an exception, a bad alloc exception, if things go wrong. Next up, we have, so that'll create our resource. Here we have our async runtime. We made 2 of our async contexts, or we want to make sure we have 2 async contexts from this thing. You pass in your resource, then you pass in how big you want each one of the contexts to be. What this will do is it'll allocate, if you ask for 2 and you put like 15, like you put like 16 bytes here, it'll allocate 2 times 16, so 32. So here I'm just taking this and cutting it in half, so I can have each context have 1 kilobyte each. From there, I know this seems like a lot, but basically from here you can then do a thing called a lease. You can basically ask for access to one of the async contexts. Then you can pass that into your functions. This is technically not necessary, but I added it in because it ensures that you don't ever have 2 contexts that like basically don't end up accessing you don't ever. The context is that these are basically these are types that have some safety added into them to ensure that you don't mix them up with other types, and they also do some other stuff. So that's what this whole leasing thing is for. But basically, you need some memory. You have a buffer resource. You can pass it into an async runtime, get your stuff out, get your contexts, and then good to go. It may seem like a lot. If you want to do like a lot of asynchronous operations, then it's the kind of thing that you'll want to know about, because this is stuff that you'll be able to control. Oh, last thing here is the handler. This is an empty handler. This is actually dangerous. You can't actually put in an empty handler, but I'll talk about that in a sec. But that might have seemed like a lot of work, so there is an alternative. The alternative would be the global sync coroutines. So the idea here, and I'm still figuring this stuff out, but basically you would have some sort of set global coroutine allocator. You can either give it memory or you can give it an actual memory resource. I'm still figuring out which one of these. I want to be able to support both, but I don't know if I can support both, so I'm going to try to support both. But the idea is that you just give it some memory and say, hey, you manage this memory. And anytime I use the house sync function on some interface, it gives me back a wrapper that's synchronous. So I can give a output pin that comes back from the get LED pin function. Let's say it comes back as a strong pointer. And then when I pass it into sync, what it'll do is it'll call the appropriate sync function for this thing, which will give me back a wrapper that utilizes the global coroutine allocator. From there, anytime I call like typical functions like level or get level, or like level and then the other level without the input parameter, and stuff like that, or configure, all of that will be synchronous, because we can basically passing in the global context to this thing and then calling sync wait and returning the values, all you have to do for each one of those synchronous APIs. So this is actually quite simple to implement. And for people who don't care about using asynchrony at all, this would be your way to just access all the libraries and call them normally without needing all of that. I will say though, before I continue, I believe it was Madeline who was most concerned about this, which was the virality of all of the coroutine stuff. And this allows you to stop the virality at this point. Anytime you have a driver, you can kind of just stop at this point. What I am planning on doing is that the sync libraries, or you should be able to pass those into resources that need asynchronous things, because this is just simply just a wrapper. You can give the underlying thing to those drivers. So you won't be locked out of asynchrony if you have other drivers that depend on it. But we will never allow any usage of synchronous libraries or the global coroutine allocator with any drivers that we write for libhal. And we will make sure that no one else, we want to make sure there's a policy that no one else uses the global coroutine allocator for the drivers either. The whole point of this is actually just to supply easy APIs for developers who just want to do stuff. It is not meant for actual libraries, because if we did that, then we would lose out on asynchrony in a lot of spots. And the cool thing about this is that you don't need to put this inside of I'm hoping if you have a single threaded application, you just have to add this into the top of your main, and that's it. Literally, this part of the function could just be it. Give it some memory, and you're done. You can just go run all the other functions, and everything just kind of works. This won't work. This will only work for things that are interfaces. It won't work for everything. Although, actually no. We could have a sync wait function that does actually execute your stuff. So we actually could make a function like this for just functions in general. So yeah, never mind. We could do that. Yeah. So this is what I would hope someone. So if you had a multi-threaded program. And you're using some RTOS to support that. My goal would be that for your main, if you just wanted to use the synchronous APIs, you just have HAL set global coroutine allocator. We give you some function called get static thread local allocator, and you give it the amount of memory you want to give. This would mean that every single thread will get 1 kilobyte worth of RAM taken up for it to have its own coroutine memory. If that's how much you want to use for that, you can use less if you don't want to use as much. And then from there, you can start utilizing all of the sync APIs and start executing your programs from that. And this is just me kind of drawing out some of the bits of how things would work. And that's pretty much it. I wanted to talk about the transition handler, but I think I'll do that at another time, at least another libhal meeting.